Okay, so let's go over this, okay? Let's see how you did. See if there were any questions. Let's see how you did. Distinguish between an embolism and a thrombosis. A thrombosis is a blood clot in an unbroken vessel, but an embolism is when it's moving, meaning it's moving through the system and you could get back to the pump, or to get to the lungs, or to get to some place where it shouldn't be. So you can talk about list 2 functions of the spleen. I wanted you to say that it is a filters blood, and that it actually stores red blood cells. Hopefully you thought you said something like that. Maybe you said that it helps to remove old, worn out red blood cells. That's where they go to die, you know. Did you think of anything else that I didn't just mention? Okay. List 2 etiologies of anemia. We learned a lot of different etiologies of anemia. We said you could have kidney disease, not releasing erythropoietin. You could be iron deficient, and you need iron to make hemoglobin, so that's going to cause a problem. You could be B12 deficient because of stomach issues. It could be because of your diet, but it could also be because of stomach issues, and that would be called pernicious anemia because of lack of intrinsic factor. You could have aplastic anemia, which hopefully you don't hear about too often because that's so awful. You can have hemorrhagic anemia, hemolytic anemia. A lot of different things can cause anemia, right? Okay, so you just have to list 2, but you need to know all of those for the test. Okay, define hypoxemia. It just simply means low oxygen blood levels, low blood oxygen levels. I mean, that's not simple, that's awful, but okay, that's what it means. When an Rh negative mother produces antibodies to the D antigen, they can cross the placenta and attack the red cells of the fetus. This disease is called hemolytic disease of the newborn, but it's also maybe more accurately referred to as erythroblastosis fetalis. Named, and you would need to know both of those, name the predominant protein found inside of erythrocytes. It is hemoglobin. Hemoglobin. And what's its function? To transport gases. What's jaundice? It's a yellowing of the skin. And why does it occur? Because of liver disease. Fair? Maybe some of you went into more detail and said that it's because the liver's not producing the enzyme it needs to break down heme into bilirubin and bilirubin and then conjugate it on down to bile. But it's because the liver's not functioning. Can we live without our liver functioning? So if we get a sign that the liver's not functioning, is that something to pay attention to? Briefly explain why the recessive faulty trait for sickle cell disease has remained in the population. I'm realizing here there were quite a few questions that might have taken a little time. Y'all finished that in a quick hurry. I hope that's because you just knew right away. And we only once. But anyway, the reason it has stayed in the population is that it's actually offered an adaptive advantage for people who live in the regions where there's a lot of malaria. That's why. If you're heterozygous for that trait, you don't have sickle cell, and you have protection against malaria. So the heterozygous state is adaptive, is an adaptive advantage. Define polycythemia. Just simply means too many cells in the blood. Were they all fair questions from last week? Were they? Would you tell me if you didn't think they were? Okay, so what exactly is Hashimoto's thyroiditis? What causes it and how does it present? What I wanted you to tell me, who wants to tell me what they put? What is Hashimoto's thyroiditis?
So autoimmune disease where the body creates antibodies that destroy T3 and T4.
There aren't T3 and T4 cells that we think like that in this situation, but you were right. You were on the track. So it is an autoimmune disease. You need to know it's an autoimmune disease where the body attacks the cells in the thyroid gland that make the hormones T3 and T4. Thyroxine. So that's what it is, and some of the signs and symptoms is that skin and hair, weight gain, just tired, lethargic, all kinds of issues can happen because of it. But okay, hypothyroidism. So okay. Just one quiz out of many, right? Just one quiz out of many. Now look, I needed to let y'all know about something that I found out about Thursday, and I haven't seen y'all since then. But I got to announce it to my Thursday class, and then by Friday I had got back in touch with the TLC. I'm going to say the TLC, but anyway, the Learning Center. They're going to do a crash course for the prep class for the TEAS test. So that TEAS test, for those of you who are trying to get in August, you only have 2 more chances at that TEAS test at the end of this month, and then there will be one in March. But, hopefully you wouldn't have to just take one because it's expensive. But anyway, there's a prep crash course. I'm so happy they're offering this. One is today at 2:30 to 4. So it's an hour and a half to sit in and just see if you can get something from it. How many of you have taken the TEAS test in the next month or two? Raise your hands high if you're taking it. So quite as many as half of you are taking this. The rest of you don't need to think about it, but this is free. It's going to be in they've assigned a room 51. Room 51 is a weird kind of room to know where it is. It's down the center hallway. If you would take a right, if you took a left, you'd be in that little math emporium lab. But if you take a right, there's a little room there. So that's room 51. There's a course today, or just a little thing today, 2:30 to 4. On the 15th from 10 a.m. to 12. And on the 22nd from 10 until 12. But the 22nd, I think we have a TEAS test here. So many of you've got 2 chances to maybe go to this. Honestly, if I were you, I'd go to both of them if I were taking it on the 22nd. It won't hurt you, right? It could only help. It's reviewing the math and the science. So how many of you are interested in that? Yeah. I would think that would be a great opportunity. Okay, so they're going to be Zooming it here. I think the tutor's on the other campus, but you'll be able to Zoom and they can hear you and you can ask questions if you need it to. But I think they're just going to do a quick little crash sort of course on it. So I'd love to know if some of you go today. I would love to know how that worked out for you if you thought it was good. Okay. Any questions for me before we keep going with our stuff? All right. Great. I have that flyer on my door of my office in case anybody wants to see those dates again, okay? All right, we're not doing the heart yet. Where are we in this? Somebody I know is going to help me here.
The last thing we talked about was thalassemia.
Oh, so we're talking about some hemoglobin disorders. Today we actually get to go into the lab. I need half of you, 12 to 13 of you, going into the lab today and looking at your blood films. Yeah, so it didn't matter. Most people got blood films, so that were here this week or whatever. So there'll be enough blood slides for everybody to see a blood film. So I just need at least 12 plus today staying, and then the rest of you would stay Wednesday. Fair? All right, so be thinking about that. All right, whether you can stay today. All right. Light cells. We've talked a lot about red blood cells, and we know red blood cells are the predominant cellular component of blood. Many of you are still confused about hematocrit. Make sure you get that before the test, okay? But anyway, the cellular component of whole blood, most of those cells are red blood cells, and we just talked quite a bit about red blood cells. But now let's look at these white blood cells, because they're not all created equal, and they all have different functions. And I've introduced you to them and told you a little bit about percentages that you would expect to see in adult peripheral blood, meaning the circulating blood that is circulating through the system. So I would want you to know that usually there's going to be a normal total count of 5,000 to 10,000 white blood cells per microliter of blood, where you all knew that for red cells, they're like 4 to 6 million, right? So red cells way outnumber white cells, but that doesn't mean white cells aren't important. You just don't have as many of them circulating. You don't need as many of them circulating. So they do protect against infectious microorganisms and other pathogens. They have a nucleus. So today, when you're looking at your blood films and your field of use are going to be mostly filled with red cells. But every now and then, you'll see this nucleated cell, and you'll know that's a white blood cell. And you're going to have to differentiate and tell which type of white blood cell it is. That's referred to as a blood differential. So we're going to take a look at those. Some have granules, and they're called granulocytes if they have granules. I don't care that you know that term, granulocyte. What I care about is that you know these names of these special kinds of white cells. And I've already told you about neutrophils and approximately how many should be circulating. And I've told you they fight against what? Bacteria. And eosinophils are big. They're the beautiful ones, the big showy ones, orangey pink granules, really huge granules, 2 to 4% circulating around. And they contain histamine. You knew that, right? And they're going to be increasing in numbers when we have allergies and or parasites, worms. So if you did, if somebody had a snotty nose and, whatever, snotty noses aren't so bad. It means that something's going on, and sometimes it's protecting you. But if you took a swab of somebody snotty up the nose and you did a slide and they were all eosinophils, what is that person dealing with? But if you did a slide of that snotty nose and they were all neutrophils, what do they have maybe? Maybe sinusitis or something it's not allergies, right? So these are slides. You can look for white cells outside of blood samples. That's what I'm trying to tell you here, is that you can look at these white cells outside, and they still are going to be there doing the same thing. Basophils have histamine, but they also have heparin. What did we say heparin does? Heparin is going to prevent unwanted blood clotting. It's going to prevent unwanted blood clotting. So that's what heparin does. Less than 1%. So most of you shouldn't see a basophil today. When you see basophils start to increase, your textbook's going to tell you that can happen in some viral illnesses. But I'm going to tell you the only time as a hematologist I ever saw basophils increasing was cancer. Is when there was cancer somewhere in the body. So we really don't want to see a whole bunch of basophils. But they're there to be. It's normal to have some, but you should see less than 1%. So that means out of every 100 white blood cells you see, less than 1 will be a basophil. Now, some of these white cells don't have granules, and so they were the lymphocytes and the monocytes. And lymphocytes, I told you, fight viruses, and they fight against cancer, don't they? So lymphocytes, viruses, and cancer, and then monocytes, we said, are going to fight against they're just going to be big eaters. They're going to be the dump trucks of our system. They're going to become the macrophages. So today, now it is true that these slides, these pictures are just classic, and they've really been blown up so you can see them at a very high magnification. Y'all's magnification isn't going to be quite this, but these are great pictures, so pay attention right here, especially since y'all are going to be doing your blood differentials in just a little bit at a time, okay? You see the red cells that don't have nucleuses, right? Almost look donut, or not donut, but almost look like little donuts, and that's fine. And then you see the cell that has these really dark, nuclear things that are segmented. This is a neutrophil. Neutrophils are often called PMNs. You don't have to write that down, but they're called PMNs on lab reports because they're polymorphonuclear cells, meaning that the nucleus has a ton of different little shapes in it, doesn't it? Do y'all see that? Where this nucleus is bilobed, isn't it? And when you say bilobed, it means there's like 2 lobes of the nucleus. And so do the basophils have that. So these are neutrophils, these are eosinophils, and these are basophils that have the big dark, they're said to be purple, but it really almost looks like black granules. You can hardly make out the nucleus, where these have really distinct pinky orange granules. So here's another slide, and what would you say that, never mind, what would you say that is? But it is, it's a neutrophil, it's a polymorphonuclear looking cell, isn't it? And with different stains, it would stain, differently. Our stains are going to look like this. We're looking at a right stain, which is the most common stain in hematology. So again, basophils with these really black granules you can see in them. And that's what we get. Okay. And little platelets. Platelets are going to be these little things that almost look like stain precipitate on your slide, but you're going to know they're not. By the way, you will have stain precipitate on your slides. But how will you know it's just an artifact? Is when you're fine focusing. It's not in the field of view. It's like either above or below. You know what I'm saying? So this is why you're always fine focusing up and down and up and down, because you can tell whether something is actually in the film or whether it's just precipitate out. But platelets can often look like that because they just don't, they look tiny and they don't look like cells. But are platelets whole cells? No, they're just partial cells, aren't they? How long do they last in the system?
72 hours.
About 96. But you can, if you donate blood, they have to give them within 72 because obviously a lot of them will be on their way out. But anyway, so yeah, they don't last long in the peripheral blood, but they certainly serve a function we're going to see in just a second. So monocytes, I told you, become these big eaters. And monocytes, can y'all see the big difference between this nucleus and the PMNs? The PMNs, the neutrophils, look like, y'all, you know how you've seen those hot dogs that are on links? You know what I mean? That's kind of what a PMN looks like. This doesn't look like that at all. And depending on what position the cell was in when you fixed the slide and stained it, it often looks even circular, not even folded like this. But it can look like this, and it can look folded, and it's just huge. The nucleus is huge. But it also has a lot of cytoplasm. No granules, but a lot of cytoplasm. So that's what a monocyte looks like. And then the lymphocyte, the difference in a monocyte and a lymphocyte, you see how folded this is? A lymphocyte is going to have a very round nucleus, really, really round. And how about the cytoplasm? Is there much for a lymphocyte? Do lymphocytes have a lot of cytoplasm? Or are they almost all nucleus? Yeah, it looks like they're almost all nucleus. And the more mature the lymphocyte, the less cytoplasm. So students, when they first start looking at their slides, they'll say, oh, that's a lymphocyte. But would a lymphocyte have this massive folded looking nucleus? No. And would a lymphocyte have all of this kind of, it's called like cut glass type of cytoplasm? No. So that's a lymphocyte. All right. Now, again, in making the process of making white cells, leuko, and leuko can be spelled with a C or a K, both are acceptable, but leukopoiesis, the process of making these, we start with blast cells. And this blast cell ends up becoming, depending on what stimulant it gets, it's going to become what you need. Now, how does it know what to become? Is because your tissues are releasing different types of hormones depending on what is assaulting them. If it's a bacteria assaulting the tissues, then what is it going to become? A neutrophil. If it's a lymphocyte that's invaded your tissues, they're going to be slightly different types of molecules, colony stimulating factors that are going to cause it to become a lymphocyte, right? If it's viruses. If it is allergies or worms, what is it going to become? An eosinophil. Are y'all with me on this? Your body's cells know what you're going to need depending on what you're being attacked by. Why is this important to know? Why is this important to know?
See if your body responds.
Oh, your body does respond correctly. Your body knows, but who might not know what you... The medical professionals might not know what's causing you to be sick. But if they are paying attention, if they're using their common sense, they can use the CBC, they can use the blood differential to let the body explain to them what's going on. You get what I'm saying? These results can come back within minutes of getting a blood draw. Within minutes. So within minutes, you're getting an indication. If the white count is up, does it mean you're fighting something? Mm-hmm. Okay, then you get a blood differential and the lymphocyte counts up. What are you fighting? Well, but it's usually virus. Because we're always fighting. Don't be thinking the worst, okay? But it's usually viruses. It's usually worse. It's usually viruses. If the neutrophil counts up, what are you fighting? Bacteria. You get what I mean? So pay attention because the patient's body will be telling you what they're fighting. And this is why it's important for you to know this. And so anyway, this is, okay. And we're going to find out that not all lymphocytes are created equal. That's to come. So just stay tuned for that because we have an entire chapter called the lymphatic system. And we'll talk about immunity. And we're going to visit these lymphocytes more then. But for right now, you're beginning your information about them so you know basically what they do. Let me say something about monocytes. Your textbook will tell you that monocytes increase in viral when you're going to see an increase in those in viral. But they're the first to increase. I don't care what's going on. So you're really paying attention to them because if they're starting to increase, it could be bacterial or viral. I'm just letting you know that. That's the truth. And they're the first ones to respond. So definitely you're paying attention to that. Guys, I want you all to know about some, and suffixes or whatever. If you see the term penia, leukopenia, it means that there's a low, there's not enough being produced. So leukopenia means there's a low number what?
White cells.
White cells. How about thrombocytopenia? What would that mean? Thrombocytopenia. That's a big word, but there's no such thing as big words. Thrombocytopenia. Thrombocytes are what? Thrombocytes are platelets. So thrombocytopenia means a low platelet count, doesn't it? So penia is meaning a low count. Cytosis is meaning that there's going to be high. So there's going to be a high count. So leukocytosis. Now, leukopenia and leukocytosis, they can both happen, believe it or not, in infectious diseases. But of course, we usually, if there's an infectious process, what do we usually expect to be happening? Which process? The cytosis. We usually expect white counts to go up. On occasion, though, there are a couple of infectious diseases that we know drop the white count. And because we know that, does that give us information? Right? So we always keep that in mind. But anyway, most of the time you're thinking about low counts because of radiation, poisons, and then certainly if you don't have enough white blood cells circulating around, if you have dropped past below 5,000 per microliter of blood, if maybe you've dropped down to 1,000, that's really low. I've seen people with less than that. Then is this person at serious risk for opportunistic diseases that can take them out of this world? Yes. So they should definitely take caution. They shouldn't be going out in public, should they? They should be making sure that they protect themselves with masks and whatnot. People coming in to see them should protect them as well. Leukocytosis is when we're going to see a high count. You can see counts in the 20,000s. And you can see really, significantly high counts with someone who has an infectious disease process happening. So we understand that. And certainly a differential is going to be really important in helping us to know what type of infection, and whether it's allergies maybe, or some other type of disease. Now, everybody wants to think the worst about if there's lymphocytosis. Lymphocytosis, what would be happening? An increase in what? Which ones?
The viral virus.
the lymphocytes, right? So a lot of people are thinking, oh, that could be cancer. No, we live in a viral microbial world. It's usually viruses. Now, but every now and then there's cancer. So anyway, when we think about leukemia, we're thinking about cancer of these white cell lines, and it can either be of the myeloid line or the lymphoid line, meaning it can be of the granulocytes or the agranulocytes. And do you think these different cancers would require different types of approaches as far as treatments go? Do you think they would? Or do you think it's all treated the same? They require different treatments. So it's important when somebody does have leukemias. And by the way, when somebody has leukemias, their white counts aren't in the 20,000s or 30. They're not there. They're a million. Their white count has gone up. Unheard of numbers, right? And the problem with this is that these cells, whether it's the myeloid line or the lymphoid line, whether it's the granulocytes or the agranulocytes, the problem is those cells are out there, but they're not mature. They're just out there as blasts, which are what? And if they're out there as blasts, taking up the space of where they should be, they're not functioning. None of them are really functioning. So is this person going to be seriously at risk for opportunistic infections? Seriously at risk for opportunistic infections, and so we understand that. Now, I do want you to know that leukemias can either of these lines can actually be called acute or chronic. So I want, as we discuss primary disease versus secondary. Primary disease means what? That's your diagnosis. That's what you have. That's your disease. We talked about primary polycythemia, which was cancer of the red cell line, didn't we? Did we? Y'all tell me, did we? And then we said secondary polycythemia is because of other things like dehydration, emphysema, other things that can be going on. Same thing with like primary hypertension. What is primary hypertension? I'm going to come back to this in a second. I just need you all to know these terms and how you use them in medicine. You'll use them all the time. So what is primary hypertension?
Blood pressure's high.
It means you have high blood pressure, and that is your disease. That's your disease. You have primary hypertension. That is your disease. Did you know most primary hypertension is idiopathic? Y'all should be writing this down because it's all stuff. It's all part of this class, and we're about to talk about the heart. So anyway, what does idiopathic mean? If something is idiopathic, what does that mean?
It's not caused by pathogen.
No. Not necessarily, but thank you. Because you were breaking that down, which is good that you were doing. It means that we don't know. It means that, the pathology, we're idiots about the pathology. Like, we don't know what's called the study of the disease. We don't know what it is. Idiopathic. So most primary hypertension is idiopathic. It's thought to be hereditary. There's a hereditary basis, but most is idiopathic. So that means if there's a primary hypertension, there means there's a what? Secondary hypertension. And what would be some causes for hypertension that the hypertension is just coming along as a sign? It's not your disease, though. Well, give me some examples of diseases that can cause you to be hypertensive.
Heart disease.
COPD can definitely do that because it puts such a strain on the heart. Diabetes, secondary hypertension. Most people who have diabetes at whatever time, with diabetes mellitus, right? They have secondary hypertension, and that's what takes their kidneys out. That's what takes their kidneys out, was their chronic hypertension. So now I want to talk about acute versus chronic. Acute diseases are diseases that come on suddenly and their signs and symptoms are severe. They come on suddenly and their signs and symptoms are severe. That's acute disease. Chronic disease is disease that comes on kind of slowly, sort of insidious. It sort of comes on slowly. The signs and symptoms are kind of, come and go, and they're not so awful, maybe. And so that's what chronic it means. Now, I want you all to know that what you're seeing up here, I'm pretty sure, is actually, this is just for adults. For adults, acute leukemias are the worst prognosis. And that's what you would expect, kind of, when you hear the term acute. chronic leukemias have a longer time that people can live and whatnot. This is the opposite prognosis in pediatrics. In pediatric populations, this is just FYI about the pediatrics. Did I tell you all pediatric medicine is a completely different beast? Pediatric medicine is a completely different beast. In pediatric medicine, acute lymphocytic leukemia is going to be the best prognosis. 90+% are cured now. Cured. Did you hear that word? Cured. So that's a better prognosis in pediatric populations. It's worse in adults, the acute. Anyway, I just want you to know what the terms acute versus chronic about any disease kind of is talking about. Usually we think of acute as certainly being worse. All right, so you get these complete blood counts and you're going to be able to see these. This is kind of going to be what your field of view is going to be looking like. And this is what it should look like. Mostly red cells, right? Occasionally in each field of view, you might see no white cells, but as you're moving your fields, you're going down your slide, coming back up and going down. You might see fields of view that have, 1 to 10 white cells, depending on what. But you see these, but mostly red cells. Look at this person. So this is not good. One of the last kids I worked on when I was doing PRN at Martha Jefferson Hospital in Charlottesville right before my child was born. And I was working nights and got called to the ER for a little 9-year-old. And I was working days at UVA, so I full-time at UVA. So that weekend night I got called in, and this little 9-year-old was being raised by her grandmother. And I remember it being like I don't know, it was cold outside. I do remember that. But the grandmother said, she's been sick for so long, and this weather would just break. This time I remember it was kind of cold outside. She said, if this weather would just break, then I think she's just going to start feeling better. So they couldn't get any blood or anything. She couldn't breathe. And do people who can't breathe want to lay down? They don't want to lay down. And her little head was back, so she was keeping her airway open, and she looked like she was kind of oxygen starved. Anyway, got the blood. Within 10 minutes, I had called in the ER doc that night and had him look, and her film looked like that 9-year-old. So she obviously got shipped to UVA that night, and the next day I went to see her, and for a couple of days after that I went to see her, but in 2 weeks she was gone. She had the rarest leukemia. It wasn't just of the myelogenous line, it was of the lymphocytic too. She had acute myelolymphocytic leukemia. And her lungs were filled with fluid. She didn't. So, 10 minutes and a blood film, you can see that. So now, those are the white cells. The white cells do amazing things for us. We want them working like they're supposed to be working, right? And we need them being just right. And just the right amounts, not too many, not too few. And they can really tell us a story if we pay attention to that story. So platelets now, they're the last of the cellular components that we want to look at with blood, and we want to be paying attention. We know that thrombocytes are platelets. We know that there's a hormone that is going to actually target the red bone marrow for stem cells to become platelets, and that hormone is thrombopoietin. And where is thrombopoietin from? This is all review. If it's not review, you're having to play catch up. Bless your hearts. Because in a class when you're doing clinicals and stuff, you don't want to play catch up. You want to be in front of the ball, right? So if you're playing catch up right now, you guys, bless your hearts, get it done. Catch up, okay? So thrombopoietin, which is from the liver, so that's going to target the stem cells and the red bone marrow. They're going to become thrombocytes, and they're going to play a huge role in controlling blood clotting. So hemostasis, not to be confused with homeostasis. That's a completely different thing, isn't it? This is hemostasis, is the stopping of bleeding, and this is going to be important. We're bleeding, we bleed so many times a day. We sneeze hard, and could we bleed to death? If you had a bleeding disorder, you could, and people have. Stub your toe, you floss your teeth a little bit too aggressively, you do whatever, and do we bleed all day? We do. We're doing something that's causing us to to bleed. But that's okay, because we stopped. Because we had hemostasis. We're able to stop bleeding when it actually occurs, and we're able to do it at the right times. Now, what I'd like you to know is, oh man, let me see if I can get to the slide I want to get to. I want to get to this slide. Because I think this slide is, okay, I don't like this slide, but okay, it's all right. Look, I want you to know that it happens in 3 stages. And this is whether you've sneezed hard or whether you've stepped on a splinter or, you know, whatever you've done. Your blood vessels, these capillaries are single file. These single cells, right, single layer. So capillaries are sitting on this basement membrane. They're so tiny that red cells have to go through them single file and be squishy, right? So as a capillary gets broken, when a capillary gets broken, something is maybe a splinter has come in here and broken it, the first thing that will happen is a spasm. And does that seem like that will be a good thing, that there will be a spasm at the site? The spasm itself would do what to the opening? Close it. That's exactly right. Or help to close it, wouldn't it? Now, what I want you to see are these endothelial cells that line blood capillaries. Do y'all see them? They're single layer, aren't they? Single layer here, these endothelial cells. They're producing prostacyclins that are repelling platelets. So if those endothelial cells are intact, if there's no injury, platelets won't stick to the walls because they're being repelled. Platelets are sticky, by the way. They are sticky in nature. But we don't want them sticking to the inner layer of your capillaries, do we? We want them being repelled, and they are. But if the endothelial is broken, then now what can stick there? A platelet. So the second thing that happens is a platelet plug. The first thing that happened was what? And the second thing is now the platelets can form a little plug. What's that blocking? The opening. You know, the opening. That's exactly right. By the way, I haven't talked anything about a blood clot yet. Don't think that that's blood clotting. That's not. They're the first 2 steps, and they are vital, that they're happening the way they should. But this third step is the step I want you to know about. It's called coagulation. Coagulation. And when you hear the term coagulation, this is what we're talking about with a blood clot. Okay? These slides. Okay. I want to get to, okay, this is what I want to get to. Coagulation. Third step of hemostasis, isn't it? And this is a blood clot. So now we know that we're ready for this third step because of that, the vessels have spasmed, closing the opening. Platelets have formed a plug, which is just temporary. That's just temporary. Now we need the third step happening, which is called coagulation. You guys, you can take a 4-credit class science course on just this slide. Now, we don't have that kind of time. But what I want to give you is the basics of this. You ready? You ready for this? Because this is really, truly is the basics of most of our it's not really. But you ready? In this third step, coagulation, the clot, I want you all to think about blood plasma. What is blood plasma? That liquid part of blood. I told you all out in that liquid part of blood, there was something called clotting factors, didn't I? I had introduced you to that there were some proteins called clotting factors. Had I not told you that? I told you that if you have plasma minus the clotting factors, if you pulled all those out, it's called what now? Serum. It's called serum, right? So I had introduced to you this idea of clotting factors. I know you all can't see this slide up close because of where you're sitting in the far back. But I had also maybe introduced the term fibrinogen to you. That's factor 1. And they're actually, these blood clotting factors are defined as Roman numeral numbers. So I don't care that you know that either, really. Well, kind of, but anyway, not really. All right, listen. But here's what I want you to know. Whenever there is a bleeding event, in this third step that's going to happen, it's called the intrinsic and the extrinsic pathways But what I would like you to know about these pathways is that these are cascading events that happen in a very prescribed fashion. And what it takes for these cascade events, these domino type of events to happen. Everybody played dominoes before? You've seen dominoes and you hit the one and it hits the next one and it hits the next one. And if you set them up just right, if you set them up just right each time, would the outcome always be the same? Yeah. But what would happen if you removed one of the dominoes? Would the outcome necessarily be exactly the same? No. No, do you get that? It wouldn't. So in your blood plasma, you have circulating around a lot of proteins called clotting factors. They must be present in exactly the right amounts. Because if they are present, then there will be this cascading event that will happen in coagulation. And the outcome is going to be you're going to get from fibrinogen to what is called a fibrin clot, blood clot. So where does the blood clot really happen? In which stage? Coagulation. What does it take to get to a fibrin clot? All of the present what? Clotting factors. If you're missing one, is there going to be a problem? If you're missing one, is there going to be a problem? Now, you guys, and I think you should definitely do this, you should look at some of these, just look at the names and be a little bit familiar. One of them's called prothrombin, you know, and whatever, but you don't have to. Listen, they're actually designated as Roman numerals. Y'all have heard of people who have, or who are lacking factor VIII. If they're lacking factor VIII, which is up here, if they're lacking factor VIII, you all have heard of this disease. It's called hemophilia. Have you? Before modern medicine, kids didn't get out of childhood that had hemophilia unless they were born into royal families. And if they were born into royal families, they could be cocooned and protected. But since most people aren't born into royal families, did they die from bleeding out, from just coughing too hard or sneezing too hard or stumping their toe? They bled out. Hemophilia, 80+% of all hemophiliacs are lacking factor VIII. And then the other percent, you know, almost 20%, are lacking one or more of the other factors. So there are many different types of hemophilia. The predominant one is lacking factor VIII. In this country, in early 1980s, I was just starting out in pathology, and we saw across the country a lot of our hemophiliacs dying. Do you know why? They were dying of an infectious disease. Do you know which one it was? Is it just that one? In the early 80s, we were seeing a lot of our hemophiliacs, many of the children, dying from an infectious disease. It was HIV. They were getting HIV because in the early 80s, now don't write this down because now we have, thank goodness, genetic engineering. We have figured out a way to get them factor VIII without giving them human donor factor VIII. But in the early 80s, that was the only way hemophiliacs could survive. They had to go in and get human donations of factor VIII. And the blood products were contaminated with what? HIV. And then they progressed to full-blown AIDS because we didn't know as much about it at the time, and certainly didn't have the treatments that we have today for HIV positive status. And so they were dying. Sometimes their neighbors were burning their houses down, the kids that lived beside them, because they were so afraid of the disease. This was not that long ago. We've come a long way. It's easy because of social media to get all kind of depressed about like where society is right now, but we've come a long way since then. Do we have a long way to go? Yes. But we have come a long way with education. So anyway, but in the early 80s, hemophiliacs were dying all over the country because of contracting HIV and then going into full-blown AIDS and dying from it, especially children. So now, though, we have microorganisms that make factor VIII for us. Human factor VIII, we can get little microorganisms through genetic engineering to produce human factor VIII and other factors, because it's just a protein. And so now, is it a safe treatment for hemophiliacs? Yes, it is. But hemophilia is a serious inherited disorder. Any questions for me about that? So it means in your blood plasma you have circulating all of these factors, these proteins that are just going to have a function that if you get injured, they're going to cascade and get you a fibrin clot, which is actually referred to as coagulation. Okay, are we good with that? Are you glad you didn't have to sit through an entire semester course for that? Okay, good. So anyway, you can't see it from this slide, but another thing I wanted to bring to your attention is that for this domino to hit this one, to hit this one, to go down and hit these, there's something that's needed in some of these steps, and what's needed is calcium. Do you remember me telling you why blood calcium levels need to be in homeostasis? Because we know that if blood calcium levels are not in homeostasis, you might do what?
Yeah.
Bleed out. You might bleed out. That's exactly right. And do you see why now? Now you know why. Because it is absolutely necessary for this coagulation cascading event to happen. All right, so how are you feeling? Now, do we need the blood clot to continue to get bigger?
No.
No.
So we said that what happened, and actually almost starts to happen right away, is something called retraction of the clot. So it is actually going to start as soon as the platelet plug starts to form and coagulation cascade starts, the clot is actually already starting to be controlled. But that is a positive feedback until it gets to where it needs to be, and then it has to be stopped, doesn't it? Okay, so that is one of those few cases that we said actually is going to be controlling that. So I've told you about hemophilia A, hemophilia B, and these are some of the other factors. The others can be more than just factor 9. It can be lack of factor 10, which is von Willebrand's disease. So anyway, but whatever. They're inherited disorders, and it is sex-linked. So what do we know about sex-linked disorders, most of them? What does that mean? It usually affects males. Why? Because the recipes are on which chromosome? It's on the X, and males only have how many X's? One. And where did they get that X from? The mom. That's exactly right. So that's why more males. Does that mean women can't have it? No, they could. They could have it. They could have actually inherited it, but it's just much more rare for females to have inherited. Okay, so I already told you what thrombosis and what an embolism is. And then infarction, we remember this term infarct. An infarct is when there's lack of blood supply to those tissues. If there's a lack of blood supply to the tissues will do what? Die. Infarcts don't just happen in the heart, which is a myocardial infarction. They can happen in many other places as well. So an infarct is just a sudden loss of blood supply to that tissue, and then it means that they're going to die. This is where that number came from, and it puts us so very high. It's really kind of scary, isn't it? So thromboembolisms. Did I tell you all about that number the other day? All right. So just another thing, and I really don't think that I really have to. I mean, I don't think I even talked to you too much about it, but serotonin. Y'all have heard of serotonin in the central nervous system being that regulator that regulates wanting to just function, right? Serotonin is that from the pineal gland. It's going to be released to help you to want to function. Wake up, get going, function. You know you've got things to do to survive that day, and just looking forward. So you get up and get going, right? And when there's not enough, and then serotonin gets converted to melatonin in the central nervous system, and that's going to cause this 24-hour circadian rhythm thing we talked about. Well, serotonin is also going to be released in times of injury by for this blood clotting, if you will. And serotonin is what causes that initial vascular spasm. So that's one of the things. So when you hear about that, then that's fine. You'll hear about that. Platelets only live for 96 hours circulating, or around that. But they're actually still producing hormones. They're producing those things. And so this is going to be all important for us to go through this hemostasis event. Now, can you have clotting disorders? You certainly can. And we're talking about when you can't clot, but you can also have excessive clots. And the excessive clots we had talked about were embolism and thrombosis. And I don't think I added it to this slide, but I want y'all to know about something. Maybe I did. I want you to know about something called DIC. Did I put it at the end? Maybe I put it at the end. I didn't put it anywhere. That's really sad. I put it on the other slide. So y'all write down DIC. DIC. DIC stands for, this is an excessive amount of clotting. So this is a problem with blood clotting because we said we wanted to stop when as soon as the vessels have been sealed, we don't want it continuing. We only want it happening in injured vessels, right? DIC, though, stands for disseminated intravascular coagulation. Disseminated intravascular coagulation. What does disseminated mean? What does that word mean, disseminated? If I disseminate information to you, which I hopefully am doing, what have I done? I've spread it all around. I've disseminated information. Have I? Y'all just lied to me. Okay, just say I have. Okay. So I've spread it all around, right? So disseminated means widespread. Intravascular, what does that mean? Inside of vessels. Intravascular, inside of vessels. Coagulation, what does that mean? You guys, does it even sound like a good thing if you're throwing blood clots all through the system? You know, we said how bad it sounded if you had one blood clot that might start to move. We said that can take you out of this world, didn't we? Right? Take your patient out of this world. But what about if you start throwing clots all over? And that's horrible, okay? And usually that is going to, again, be a cascade event that happens, and patients don't usually make it. When they do make it, they are very, very lucky that they make it. Usually when it's happening, it happens suddenly. And you can actually see it happening on a patient where you're seeing they're starting to become cyanotic in the extremities, and that cyanosis is actually continued. What does that mean, cyanosis? Cyanotic means what? Bluing or darkening because of lack of blood supply to those tissues. They're turning dark, they're darkening, and you can actually visibly watch it happening. So when someone survives a DIC event, which is an emergency event, they're very, very lucky people. So they're going to be given huge amounts of anticoagulants that end up becoming, it's just such a fun, it's such a crazy thing because this is what's happening to them. They're throwing clots, so all throughout the system in these small vessels. So tissues are suffering and becoming hypoxic. The tissues are dying, right? But at the same time, they're bleeding out. They're bleeding out of like mucous membranes and from areas because the clots are going toward those unnecessary coagulations and not staying where they might really need to be. So it's just a horrible event that happens. It can happen because of infectious diseases. There's some infectious diseases that we know that this is what we really worry about, or DIC events. And then it can also happen on rare occasions after delivery. And it can happen a couple weeks after delivery. So obviously it's pretty rare for that to happen, but it can happen. And really why it's happening is not directly known, except that a woman who is in the third trimester has about 30% extra blood volume that the system is dealing with. And then they deliver, right? And is that blood volume then going to be going through these things where it's trying to get back to equilibrium. It is really, and so it can happen in those cases too, which is not good. Usually doesn't end well for the mother or any of the patients that have it. So DIC is just not something you usually want to hear about, and it's has a really high mortality rate when that happens. So excessive clotting. All right. So let's see what else. So we talked about preventing. Well, we didn't really talk about this, but these are some of the things that can be done in managing blood clotting. So preventing formation of clots or dissolving existing clots. So these are some of the things. This is kind of FYI. Not really going to talk about it too much. Do leeches still get used?
Yes.
Yes, medicinal leeches, but they do now have mechanical ones, but I think mostly they're still using the medicinal ones. All right, streptokinase is an enzyme that is produced by a bacterium, and TPA. I do want you to know with these two, you have a clinical insight about streptokinase and TPA, tissue plasminogen activator. These are great. They can be used to burst a clot, especially if somebody's having a heart attack, but they can also kill you. So if you don't use them in the right time event, supposedly if somebody's having a massive MI, massive myocardial infarction, these have to be used within the first 30 minutes to an hour. If it's much after that, and they're dangerous even if they're used then, but is a heart attack maybe going to kill them anyway, right? So you've got to try to burst that clot. And then, anyway, so those are just some of the things that can be used. One from bacteria, produced by bacteria. So how about that? Y'all feel okay? It's on your PowerPoint, right? It's in your textbook. None of this made up. It's all in your textbook, okay? All right, so let me ask you something. I'm going to do a little introduction here. The heart. We just talked about the blood. Is the blood? Did y'all find that interesting about blood plasma, but also about the cellular components of blood and everything that's going on, what the blood is delivering to our cells? Because you know, our cells are stationary, so they're required for the blood to be able to get to them, bringing nutrients, still picking up waste, and we'll talk about the excretory system, how the skin is an excretory, respiratory system excretory, the urinary system is excretory, even the GI systems. We get rid of waste this way, but it's the blood that's moving things around. So how is the blood moving? Can the blood ever slow down, or does it have to keep moving? It has to keep moving. So what's moving the blood? The heart, because the heart's a pump. Is the heart a pump? Who says the heart is a pump? Raise your hand. The heart's a pump? Some of you aren't playing, okay? So you're wrong. Thank you, Janet knows I was going to say this. Everybody thinks about the heart's a pump, and I say the heart's a pump. You know, we do say that, but that suggests that the heart is just this one pump. It isn't. It isn't. And for nevermore can you think of it that way. Not ever. Don't think of it that way. If you do, you really don't understand the circulatory system. The heart is a two-pump system that just happens to be working in complete synchrony with each other. It's a two-pump system that is working in complete synchrony with each other, and it had better be working in complete synchrony because the vessels are a closed system. Those two pumps are pumping blood into vessels that are a closed system. So if one pump started being more effective than the other pump, then what's the blood going to do? I was trying to think about two pumps pumping blood in a closed vascular system. That means it better be staying equal because the two pumps working in synchrony, because if they aren't, if one is outpacing the other, then blood's going to back up in one of those systems, isn't it? Does that sound like that would be a good thing? Blood backing up in one of your systems? Because if blood is backing up in one of the systems, it's going to get more time for osmosis and other things to happen, and water movement, and that's going to cause problems. So first though, we're going to look at what should be happening in a normal situation. And in a normal situation, your heart, which is two pumps that are working in complete synchrony, are going to be pumping blood effectively so that it is moving at the right pace. It is moving at the right pace through the system, and it's going to be able to do its job. Because that's really what the heart is all about, is getting that very important blood that we just learned about to be able to do all the functions we just talked about that blood does, right? We haven't really expanded upon the getting rid of waste, but we will do that in the next organ systems. But anyway, let's look at this pump now that we know is not really a pump. It's two pumps. And I need for you to be thinking about this with these, and maybe there's a picture here I would want to show you. You guys, everybody comes into this room knowing that your heart has 4 chambers, or should have 4 chambers, don't you? Don't you know that? And there are 2 upper ones and there's 2 lower ones. I think everybody knows that. Now we're going to name them. The 2 upper chambers are called the atria of the heart, and the lower chambers are called the ventricles of the heart. The upper chambers, you've got a right atrium, singular, and a left atrium. And the lower chambers, you have a right ventricle and you have a left. Okay, so I want to show you guys where these are. So on this picture, this is the right side of the heart. This is the left side of the heart. Is that right? Left. No, left. This is right. Because we're looking at a heart in an anterior position. Y'all know anterior position, right? So from the front, an anatomical position. We have taken a coronal slice and we've removed the front part of the heart. So we're looking inside and we've got 4 chambers. We've got the right atrium, the left atrium, the right ventricle, and the left ventricle. Fair enough? Well, here's what you've got to be thinking about. The right pump, which includes the right atrium and the right ventricle. The right pump is sending blood to your lungs. So the right pump is called the pulmonary pump, because pulmonary means what? Lungs. The right pump is sending blood to the lungs. It's called the pulmonary circuit, the lungs that it's sending to. How far are the lungs away from the heart?
Not far.
Are the lungs very far from the heart? Okay, hold on to that thought. This left pump is called the systemic circuit pump. Systemic circuit pump, because it's sending blood to the system. Are you with me on that? And when I say the system, I mean what? I mean to your fingertips, to your toenail cells, the cells in the beds of your toenails, to your hair follicles on your scalp. It's sending it to your kidneys. Don't your kidneys need oxygen? Hey guys, actually doesn't your heart itself need oxygen in your heart part of the system? So the left side is called the systemic side because it's sending blood all throughout the system. Now when y'all think about a heart, when you think about a heart, we understand it's got these chambers, right? Right? We understand that the upper ones and the lower ones. But we don't ever think about this as being a pump anymore because it isn't. It's what? It's 2 pumps. This right pump is sending blood just to the lungs, which aren't very far away. But this left side is sending blood, like I said, to everything else. Everything else. Actually, the lungs need nourishment. Right? So it's sending to the system. would it make sense to you that if I did a sagittal section of a heart, meaning I separated the right from the left side, would it even make sense to you that this heart muscle would they be equal looking? Would the muscle on the right side need to be as thick, as large as the left? Actually, if you do an autopsy on somebody and it is, that person had disease. So no, it shouldn't be. And we'll talk about what that disease is in a little while, but no, it shouldn't be. Because this right side is the pulmonary circuit. It's sending blood to the lungs. What do you think the right pump is sending the blood to the lungs to do?
Get oxygenated.
Get oxygenated. Something's on hard right. Did I tell you I did science because it's easy? You know, that all makes good sense, right? So to pick up oxygen. And to drop off what?
Carbon dioxide.
To drop off carbon dioxide. Really? Does everybody agree with that? And if the left pump is called a systemic pump, what's it delivering to all the tissues?
Oxygen.
And what's the blood doing when it gives off oxygen? It's picking up what?
Carbon dioxide.
So what you just told me is that the right pump pumps blood to the lungs. The left pumps blood to everything in the system. Is that what you just said? So what would it make sense for you is where blood is coming back to the right side. When it's coming back to the right side, when it's coming into, by the way, blood enters the heart to the atria. So when on the right side, where is blood being brought to the right side? Where had blood been? It had been to the where? It had been to the where? The system, the body. And it delivered oxygen, picked up CO2. So this is coming from the system. I can't write because they don't have me. So guys, let me say this. So the right pump is receiving blood from the system and sending blood to the where? And the left pump is receiving blood from the lungs and sending blood to the what? System. Okay, so now here's what I need you to know too. Blood comes into your pumps, into the atria, and the atria fill. Y'all see them filling? Mm-hmm. Because blood is coming into them, and they're filling. And blood gets ejected. Blood gets ejected from the ventricles. It gets ejected out of the heart from the ventricles. You must know that. You must know that. You must also know this, that the vessels, now listen to this, the vessels coming to the atria, y'all said that vessels that enter into the atria are bringing blood to the heart. Did y'all say that? Those vessels are called veins. They're called veins. Veins bring blood to the heart. Veins bring blood to the heart. When veins bring blood to the heart, I'm saying this in a lot of different ways, hoping that you're kind of picturing it. When veins bring blood to the heart, what were the chambers that's receiving it? Atria. See them filling? Everybody have your atria filling. Let me see them filling. Thank you, Sarah, for playing. Sarah, play. Everybody's atria fill. Atria are filling. They're the upper chambers. They're filling. Filling. Veins are bringing blood to the atria. When the atria contract, they're sending blood to the ventricles. When these atria contract, see these little atria up here? When they contract, where are they taking blood? Where are they pushing it to? To the ventricles. And the ventricles contract, and they're sending blood away from the heart by way of arteries. Arteries carry blood away from the heart. Arteries are receiving blood from which chambers? Does it make good sense? The right ventricle, would it make sense to you that this right ventricle since it's called the pulmonary pump, as it's sending blood into this vessel, this is an artery, and it's called the pulmonary artery. Well, what a beautiful thing for it to be called, because what circuit is that? The pulmonary circuit, isn't it? We don't memorize any of this, so we make this make sense. And this left ventricle, when it contracts, it's going to send blood to this aorta, and the aorta is going to send blood. That's an artery. Have y'all ever heard that the aorta is your main artery? Have you heard that? Mm-hmm. Because it's receiving blood from where? It's receiving blood from where? Left ventricle. The left ventricle. And the left systemic pump is going to then, that blood's going to end up going to the system. This aorta has a lot of little things coming off of it. Right here, this little arch, aortic arch. If you're a little red blood cell and go this way, you're going to go up to the brain. You're going to go out to the arms maybe. But if you take the curve and go down the descending aorta, you're going to end up nourishing the what? Lower part of the body. But you got this arched aorta and you got the descending aorta, and that's received blood from that left ventricle. Isn't that right? The systemic pump. Two pumps. I'm going to let y'all go in a second, but think about this. The atria have to fill exactly in synchrony and contract when they in synchrony. When they contract in synchrony, they're sending blood to the where? Ventricles that are filling in synchrony and contracting in synchrony. Boom. Do they have to be working in synchrony?
Yes.
Do they? Must they? Because we're going to talk about times that they don't and how bad that is when they don't, okay? But they must be, because it is no longer something you think about as a pump, is it? It's a what?
Two pumps.
It's two pumps. The right side being the what circuit? And the left side being the what? Vessels that bring blood to the atria are called vessels that carry blood away from the ventricles, away from the heart, are called arteries. I just saw a test question on the nursing test that said arteries carry oxygen-rich blood, and it was stating that arteries do. Do all arteries carry it? Which is a really poor question. And I was hoping some of my students were going to say, throw that out, because that's not true. Do all arteries carry oxygen-rich blood? Which ones don't? The pulmonary arteries don't. Because they, from the right side, they're sending it to the lungs to get, hasn't gotten to the lungs yet, has it? To get oxygen. Okay, so how do you feel? We're going to pick up here on Wednesday. Y'all have enough to do something. Hey guys, those of you who aren't using, are y'all using the study guides from your peers to help you with your notes? Some of you aren't. And I know you're not, because of the timing of when you do the study guides. So you know, that's just a resource that you're letting go by the wayside. Remember, I see some of you in micro. But remember, there is a crash course on this TEAS thing from 2:30 to 4. It's an hour and a half. You wouldn't have to stay the whole time if you didn't think it was doing what you needed. But anyway, it's in room 51. I need at least 12 people staying today to see their blood films. Raise your hands. I need 12. I don't need a whole lot more than that. 1, 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 is fine. And the rest of you will do it on Wednesday. It's not optional. Okay, so the rest of you will do it Wednesday. Thank you.